We have the UNCW Undersea Vehicles team with us today. We have Jason with us. He is an ROV pilot technician for the UVP program at UNCW. He received his BS in Marine Science and Meteorology from NC State in 2008. And after graduation, he worked for C&C Technologies as a hydrographic surveyor in the Gulf of Mexico, conducting NOAA marine debris surveys and oil and gas surveys. He then worked as a satellite oceanographer in the commercial fishing industry for Digital Globe in Herndon, Virginia. Jason has been with the UVP for 10 years and has completed 44 ROV missions, 535 ROV dives, and has spent more than 973 hours on the bottom piloting the ROV. Samantha Flounders graduated from the University of Hawaii at Manoa and received a BS in Marine Bio in 2015. After graduation, she operated boats on Kaneohe Bay and then in San Francisco Bay. She then joined the NOAA Commissioned Officer Corps, where she was an officer of the deck and the navigation officer operating NOAA's research vessels throughout the Gulf, Atlantic coast, and Caribbean. She met the UVP team while working for NOAA and has worked underway with them in different capacities over the last few years. She joined the UVP team last field season. Jason and Samantha, take it away.
Thanks, guys, for joining us this afternoon. My name is Jason White.
Thanks for that introduction. I'm Samantha Flounders.
And we're going to tell you a little bit about our program this afternoon. So what we use remotely operated vehicles for, so the main reason why we use them is they're a lower risk. So if you put a manned submersible or a scuba diver down, there's always an inherent risk to the actual human being down there. With our ROV, we of course control it from the deck of the vessel or the inside of the vessel, and it's just equipment underwater. It also allows us to maximize seafloor bottom time. So a lot of days we'll go out and put the ROV in at 8 a.m. in the morning, and we can stay down till lunchtime, come up for a 20-30 minute break, and go back down till 5 or 6 o'clock in the afternoon or evening. So we can cover large areas in a short amount of time. So another great thing is real-time video input and researcher input. So we work very closely as pilots with all the researchers we go out at sea with. And basically, while we're operating the ROV, they show us which way to go, what we want to do, and all that kind of stuff. Especially lately, the last few years, what has been a really big deal is sample collecting. So we're doing a lot of sample collections. I think last year we had like 1,700 and something samples. So they're speaking in our ear the whole time, telling us to go here, go there, and look at all the different stuff they want us to collect. So here at UVP, we have 3 main items that we operate these days. We have the Mohawk 18 up there at top. We have the Phantom 300, which is a small ROV we can run on our research vessel here at UNCW. And we have a glider AUV, which is currently loaned out down at Skidway in Georgia. We acquired the Mohawk 18 back in 2013. And before that, we were using a Phantom S2 since 1987. So the program's been around for a few years now. So this is a short video of a time lapse of a day in the life of an ROV pilot. This is out of Galveston, Texas on the RV Manta. And that's us preparing in the morning to put the ROV in the water. Here's all the scientists inside with all our equipment. The pilots over there driving in the corner, and the scientists are doing the manipulator and things like that. This is an electric manipulator, so it's actually really, really slow in real life, but that's our bio box that we can go in and out and put different staples in different drawers to keep them separated for DNA purposes. There's a picture of our tracking, so you can see the ship and the ROV moving around, so everything's georeferenced. Of course, the ship captain driving around backwards on the Manta. It's no DP on that vessel. Here's us bringing our umbilical in at the end of the day, putting it back on the deck. Here's the scientists unloading all the samples they collected during the dive and processing them in the lab. And then every day we, of course, put all our equipment away so it doesn't get blown over or washed over at night. So we're storing the RV back on the deck and all that thing. And we all got to eat at night, so grilling out some hot dogs and hamburgers that evening. All right, so what we primarily use ROVs for our photo and video documentation. That's our primary purpose for ROVs. What we do is we record HD video and we take digital stills photography of whatever the scientists want. So sometimes they want habitat characterization, so we'll put the digital stills facing straight down and take photos every 30 seconds, every minute. and put lasers in it so they can get a distance, basically the distance of the photograph or the area covered, and do count coral or something like that. And we're also doing HD video, and everything is georeferenced by time. So we use these items for high resolution and habitat characterization, ground truth, multi-beam side scan sonar, and fisheries. We do a lot of fisheries work. And like I mentioned earlier, we do a lot of sample collections the last few years. We do cruises. Sometimes we're only getting sponges. Sometimes we get coral. You never know. The top left up there, you'll see a laser going down, the two green lasers, and then there's a block there in the picture. That's a 50-pound cinder block that we put down there for long-term monitoring. So we took it down on the RV, placed it on the bottom, and we go visit it once a year and take a picture of it. So that's another type of item we do. All right, so documenting ocean health using digital stills. So on the left here, you'll see oceanographic coral. There's a big marine protected area just east of middle Florida, from like Fort Pierce on up to like Cape Canaveral. And there's a whole area that was dragged for shrimp back in the late 80s. And there was tons and tons of live oceanographic coral there prior to that. And the white coral, there's a live, like hard rock coral. I think the depth's like 400 or 500 feet in that area. And after the trawlers move through, they basically kill it all. They crush it because once the trawler hits it, it just breaks up in small pieces and looks like that bottom left image. So that's one example of habitat kind of characterization using digital stills. Another example is off North Carolina here, about 75 miles, is a wreck called Snowy Grouper Wreck. And it was made of basically put inside a marine protected area back in the, I think it was around 2010 timeframe. And they documented, or we've documented over the years, the amount of snowy grouper on it when it was first made into a marine protected area compared to it was, several years after a marine protected area. And now if you go there, there's hundreds and hundreds of big monster snowy groupers on it. So you can see that bottom image there, quite a few snowy groupers on it. Pretty cool. Another example of using video footage to document items is this High Island oil platform is located in the Flower Garden Banks National Marine Sanctuary. And it was there from, I think, the 60s or 70s. And then about 3 or 4 years ago, they decided to finally remove the top 60 feet of it. And we wanted to do a pre and post survey of the platform to look at the environment and see basically what happened after they cut it off. So we took the RV that goes all the way down to 440 feet. It's muddy at the bottom. You can't really see the last 20 feet, but it's pretty interesting, the amount of habitat and the sponges and the corals and stuff growing on it and everything living in the area. I think East Flower Garden Bank is like a half mile from there, so it's really close to all the coral reefs and things. But you can see the lasers in the image. We're using those for scaling. So that's 10 centimeters apart. So anything you hit with those is 10 centimeters, and you can kind of get a judge of, if you take a screen grab of the video, you can see how big things are. So this is the Mohawk ROV. So we've changed it quite a bit. It was originally purchased from Sub-Atlantic over in Scotland, and it had plastic sides on it. It didn't have the bottom portion of the collection skid. The orange syntactic foam on top was yellow. It was completely different. So we made it an open frame design, so it was easily to work on. We can get in there and do whatever we need to do in the field and change things really quickly. And then Harbor Branch Oceanographic Institution built the bottom collection skid portion for us back in 2015. And basically it has a bio box, so we can open a drawer, put things in there with the manipulator. It has a suction hose and it has a carousel on the back with 5 2-liter buckets. So we can go in and grab little things and suck them up the hose, or grab the larger things and put them in the bio box. It was designed around the Johnson Sea Link capabilities, but of course much smaller, since this is a observation class ROV. The syntactic foam, we increased that quite a bit to make much more flotation, because the ROV is now quite a bit heavier than we originally purchased it. We of course have a HD video camera. We have 2 digital stills nowadays. We can put one on the skid facing straight down and still have one on the tilt bar facing forward. And we have 5 thrusters, 4 horizontal and 1 vertical. Right now our depth capability is 300 meters. We're going on a cruise in July, and it'll be we have a new winch. We're going to go to 530 meters, and hopefully next year NOAA's going to support a advancement to 1,000 meters of us getting a new winch. So that's our depth capabilities currently. Here's some of the potential samples we get. Corals and sponges and shells and rocks, and lots of algae and algae nodules for that type of folks. And really whoever hires, they want to go out and get a particular thing, and we can get a lot of those type of samples. Here's a little bit more about the collection capabilities. The 5-function manipulator is all electric, so we can pretty much, it's pretty strong, get quite a bit of stuff. We were just out doing a mission for Scripps off Virginia Beach 2 months ago. We're trying to cut some line down at a couple hundred feet. And so we had difficulty cutting some line that was 3 inches thick. But for the most part, anything 1.5 inches in diameter or less, we can cut it pretty easy with a razor blade sampler. And we've really mastered the skill of cutting soft corals and picking up sponges and stuff like that, because we do that quite often. So we also have a CTD mounted on the ROV, so we do CTD measurements at all times when we're using the collection skid. Here's a little cool video of some white sharks we saw in South Carolina a couple years ago. Figure we had a couple cool videos in our presentation because we all like that kind of stuff. So the first one was a smaller male. This is a bigger female. I think the first one was like 400 something feet down. This is 250. So never know what you're going to see down there with the ROV. We come across a lot of weird things. So like I mentioned earlier, we do tracking at all times at the ROV. So anything we do underwater is georeferenced. So basically we hang a hydrophone off the side of the ship, and we have a transponder on the ROV. And at all times we're recording data when we're in the water. And the way we do it is we use a Excel and HiPack and basically record the time and the georeference and the GPS, and it brings in the tracking data. So that bottom right image, you can see the straight line is actually the ship, and the squiggly one is the RV running around on the bottom. This really comes into place when we collect things or put markers on the ground, or we need to come back to a certain area and look at something again. So it's very important for all the scientists. Here's an example of multi-beam operations where Sam and I will be heading to St. Thomas in 2 weeks to go work down there for a few weeks on a NOAA ship, Nancy Foster. And basically we'll be doing this project right here. So the ship will be multi-beaming from 5 p.m. until 7 a.m. every day. And during the day of the ROV be in the water doing habitat characterization and ground truthing. So what we'll do is chief scientist will pick places out that look interesting to him, like that shipwreck there on the top right, or other features. And he'll go down and we'll confirm with the ROV and just run lines basically all day long. And then he can also look at a backscatter from the multi-beam, and they develop models and actually be able to, we're proving what the model output is. It's pretty interesting. He's been working with Tim Batista out of Silver Spring with NOAA, and we've been doing that for this project since the early 2000s, 01 or 02. So.
Hey, I'll take it over from here and tell you a little bit more about the operation. These are the ships that we get to frequent. On the top, you've got your NOAA research vessels, the White Holes, that's NOAA ship Nancy Foster, and the Pisces. And on the bottom there are some of the university research vessels that we work with. The Manta that we were talking about out of Florida and Banks, and the Walton Smith, which we actually have a good video of coming up next. But as well, here's a easy map of the ports that we frequent as well, the entirety of the Gulf, down the East Coast. We get to spend good time in the Caribbean. And as well, we drive all of our gear to these places. So in the top left picture, there's our truck and trailer, the ROV, the umbilical cable, everything Tetris loads up nicely with just a little bit of space to spare. And we drive 18 plus hours all around out to New Orleans, Cocotree, to all of the different ports to meet the different vessels that we travel on. And here's the video of a nice drone video, nice, calm, clear day as well. Back deck launching here.
So this, for 5 years, the UVP team worked with CORT, which is out of Harbor Branch, a team down there, and we worked on a collaborative mission with several PIs from different universities. and we were down there doing habitat characterization of Polar Ridge. So this Polar Ridge is about 80 miles west of Key West out there, and it's pretty flat. It's only about a 3 or 4 meter range in height over, I don't know, 50 square miles or something. So it's pretty flat out there. But there's tons and tons of plate coral, and they want to do analysis of the plate coral in the area and also look at the different sponge diversity. Harbor Branch does tons of biotechnology stuff with the sponges. So that was our main goal, to kind of go look at all that. We went back on the Anella cruise and collected all the sponges, a whole bunch of them. But they had a lot of red grouper pits down there too. So the red grouper, they're about 3 or 4 meter wide pits and 1 meter deep, and they're pretty interesting. So a lot of lionfish living in the area in the red grouper pits. Saw tons and tons of algae. I think the whole depth is about 55 meters to 70 meters is the typical depth of the Polar Ridge area, somewhere around there. If I recall, we haven't been there since I think 2018 was our last year going there. But you can see that it's really great visibility and tons of different types of sponges there. So. Lots of algae. Got the big leafy red algae. We can suck that up in our collection skid using the suction hose. We put it on really slow and it can go right up in there. So there's a little agaricida plate coral there. They were very interested in the population of that. So. And I call that pretzel coral. I forget what the real name is. That's Swiftia. We've been collecting that the last few years on our work with NOAA down in the Gulf of Mexico. Large amounts of lionfish, unfortunately. So we haven't figured out a way to kill them yet with the ROV. There's a spawning aggregation of sea urchins. Pretty cool.
All right, and I'll tell you some more about how we launched the ROV. Nice image here, an animation of ship Nancy Foster. And this is just showing the downweight below gives capability for the ROV to stay pretty much stable in the water. The scope that you can see at the bottom is about 100 feet out. And you see the ship is pretty much directly on top of the ROV. So as much as your scope runs is the distance that you'll have to travel. And as the ROV pilot, you're in constant communication with the bridge, telling them, need you to move 2 meters northeast, and slowly just navigating them step by step to travel with you. As well, on the scope that's 100 feet out, we've attached some these black ear trawl floats, and they make it so the umbilical cable, which instead of being negatively buoyant in the water, actually is neutrally buoyant, so that scope line behind us has less of a chance to get hung up on stuff, to get wrapped around things. We've got some good pictures coming up just of the hazards of those type of things. There's a good picture there on the top right of the cable that's actually wrapped around a rocky outcropping. And so this is something we're always diligently aware of, is the surrounding marine environment. Obviously, there's a lot of fishing line we watch out for. Don't go near any of that stuff. A lot of shrimp nets. The picture on the bottom right is the ROV coming back into the ship, and that's a pretty scary image sometimes when you see the propellers usually not spinning. They're just kind of free spinning, but the hazards that we are constantly aware of, the hull of the ship, the propellers, lines. The one in the bottom corner, the bottom left there, is some sunken barges, and we navigate around those with extreme care. Other things while we're underwater to take concern about, be aware of, is the visibility, current, waves, light. There'll be certain dives we're on where the current's ripping out of a certain direction at about a knot or two, and we'll be trying to stay on the transect line, and you'll just have to find the exact right angle of approach to navigate the line and hold a steady heading. Of course, we don't use anything like autopilot, so as the pilots ourselves, it takes good concentration to really hold focus and navigate a straight line, depending on what the conditions are below the water. Sometimes we'll have beautifully tranquil dives. It's an easy day. Other times get a little battered around. But yeah, and also, the picture up here, the top right is marine sediment that either we've kicked up or a creature has kicked up. And you know how long, if you're a diver, you know how long it takes for that to settle and you to have clear visibility again, or some, form of visibility again. Of course, we see tons of beautiful, interesting, fascinating, colorful creatures on all of our dives. The top right up there is an interesting sponge. We've got lobsters, spiny oysters, soft coral. We spend a lot of time snipping and collecting the soft coral in the bottom center there. Starfish, lots of beautiful creatures we hang out with, just like this one. Yeah, got an octopus here that's feeding. So it's nice to kind of be able to intercept underwater creatures in their daily lives and really be able to see what they do on a daily basis. Fortunately, we haven't scared this octopus off. Other ones we've been in a chase pattern with as we've scared them and just trying to get good footage of them. But fortunately, we haven't scared him off too much from his meal. Other creatures we see a lot of fish, sea turtles, eels, stingrays. We have plenty of fantastic photos of fish. Sometimes actually too, when we light the strobe camera off, it blinds them for a little bit, which is a good way to be able to capture photos when they're a little bit blinded, get another good shot of them. Unfortunately, and absolutely, we see trash, garbage of all kinds, you name it. We see it down to the deepest depths, solo cups, beer cans, chairs, tires. It blew off your boat. We found it in the ocean. Unfortunately, these aren't really in our capabilities to bring back oil drums or anything like that, but we do encounter them more often than we'd like to. On a more positive note, though, we also encounter lots of different forms of marine life as we spend a lot of time outdoors on boats across the ocean. I'm sure you guys have seen the dolphins playing in the bow wake, sea turtles surfacing. Here's a good scientist friend of ours, John Reed, who has the largest heart for taking care of the migrating birds that sometimes go off track, or they're flying out too far and they see the big ship and land down, and they'll spend hopefully they'll spend the entire time out there with us, but we've had a few burials at sea for the birds that get lost on their way. And of course, we see spectacular weather events, plenty of fronts moving in, water spouts. It's always an interesting day out on the ocean, spectacular sunsets, sunrises. That's one of my favorite parts about the job, is that you are exposed to all of the natural events that when you're on land, covered by the trees, the mountains, whatever, you don't get the full horizon view of everything. I feel like we have front row seats to some of the most fascinating weather events. Speaking of which, we got struck by lightning on our last cruise on the Pisces this summer, which was a novel experience for all of us. Other challenges about working aboard a boat is obviously you're on a moving platform the entire time. These pictures here, the lower left there is just, imagine thousands of pounds being lifted up in the air on the back of a ship and moving around. We will call operations in certain weather conditions and say, no, today is not a day that we'll be putting the ROV overboard into the ocean. So it's good for us to make calls for different wind conditions, weather conditions, wave conditions. But a lot of the time we work with the ship captains and see if the ship can hold and make it happen if we can. Here's a great video just depicting the magnitude of swell. It's hard usually to get a gauge of how big the seas are with a camera, but as you can see, the back deck is moving up and down 8+ feet. and just take in, yeah, you can see the whole shape there as everything. It's quite a wild day to be working the back deck. Here's a nice time lapse of our topside equipment and the intricacies that go into setting up all of our navigational equipment, all of our tracking equipment, all of our video and recording equipment. And so every time we leave for a mission, we'll undo everything at the lab. Every time we get to the ship, we'll put it all together. Every time we get back, we'll be in this situation, putting everything set back up again.
And the gentleman doing this he's our old coworker, Eric, the gentleman that was here before, Sam, basically. She took his position over, so he's in a couple of videos. So probably good.
Yeah, it's great with the time lapses. There's some good little artistic touches there, box moving in and out, last little things. And so here's a good just layout of all of our topside equipment. Here is set up on the Manta. And where the 4 screens are on the left side, that's where the pilot sits. We've got our hand controller there on the table. Excuse me. Next to that is the screen grab computer. So as you saw in the time-lapse video in the beginning, we'll have the pilot in here, and then the scientists are all around us as well, taking photographs, pointing which direction they'd like to go pick up that, go sample this. So it's a very immersive experience for the scientists and anyone else aboard. Everyone gets to be part of the operation because everyone gets to see the live footage coming back to the vessel. Here's just some more pictures of the annual maintenance that we do on the Mohawk 18 ROV. You can see in the bottom right is the frame itself. So that means literally everything that's inside of the frame is outside of the frame, separate from the vehicle. About, once a year, everything comes out, everything gets cleaned, take it down to the bare bones, nuts and bolts, scrub it, re-oil it, re-grease it, put it all back together. And that diligence of practicing good maintenance is something that keeps the ROV in great running condition throughout the season when we need it to be functioning properly, although things do break all the time. Here's another fun time lapse that our coworker Eric made of just a thruster maintenance, breakdown, repair, put back together, a full stator replacement. So pretty much every piece gets this nice fine-tuning detailed work during the winter time, and that's what we've been doing for the winter time. Here's just a nice summary of where we are today with the UVP program. Over 3,000 dives completed, over 4,000 hours underwater, a bunch of photos taken. We go on a lot of different vessels, work with tons of different scientists. Longest time we've been down, there was probably a few bathroom breaks in there, 10.9 hours, and the deepest dive, which we're hoping to actually beat, go deeper this summer with our new winch system past 1,000 feet. And yeah, that pretty much wraps it up for us. Thanks for your time today. If you've got any questions, shoot them at us, and thank you.
I got a question about the looked like a green laser, a couple of green lasers you're using for ranging. I'm just curious about it. What kind of a range can you get underwater with a laser? How fast is it attenuated?
Well, they're not really used for ranging, to be honest. So we have a set of green lasers and a set of red lasers. They're used for scaling purposes. So we're not really looking how far we can shoot them underwater. We're looking for if we hit something with them, then we know that's 10 centimeters apart, basically. So the green ones are 50 milliwatts. They're pretty strong and they scare all the fish away, to be honest with you, besides like 1 or 2 species. So they will go pretty far underwater. It all really depends on the conditions, on how clear the water is and everything like that. But really the primary purposes of the green ones is to shoot with the digital stills photography. So when the people use like coral point count and things like that, they can see the two green dots and they know that's 10 centimeters and they can do the area in the photograph and things like that. So,
Okay, thank you.
You mentioned that you use a hydrophone to georeference the vehicle by time. What's the accuracy on that? Do you have an idea?
Yep, so that's a good question. That depends on a couple things. So right now we usually use a Trimble dual antenna SP461 Trimble GPS system. And that's a differential system. So we're good to that to about a meter. If we're getting differential wherever we're at, for somewhere around the United States, we usually get differential. So if that system's good to a meter of accuracy typically, and then the hydrophone system is dependent on depth. So I think around 100 meters, 150 meters, half our depth, our typical depth we're diving, it's good to about 1.5 meters. And I think at 3 meters, 300 meters, it goes down to 2 meters accuracy. So at our max depth of 300 meters that we've been doing the last however many years, you have that 2 meters plus the 1 meter from the GPS antenna. So that's up to 3 meters accuracy depth at 300 meters. Now that could be greatly improved by a lot of the NOAA ships we're on, the Foster and the Pisces and some of the other ones. They all have POS-MV systems, which are extremely accurate GPS systems down to like, 10, 15 centimeters. So if we're doing that, then we lose the 1 meter from the Trimble. So then, you're really less than 2 meters at all times with the ROV. So good question.
Thank you. Is there one in the chat?
I believe there is. This one is from Janet Unot. Very interesting talk. 3 questions for you. And I'll just do one at a time. Where/how is the CTD mounted such that it stays safe, but the measurements aren't fouled by the ROV's thrusters?
Yeah, the CTD is mounted on the starboard side, as we saw the open frame system. It's just inside. Yeah, if we've got that picture, it's even better. But all of the thrusters are clear. All of the cables, we always keep clear of it. Yeah, it's actually across the way. It's hard to see there. But as you can see, the thrusters on this port side mimic the ones on the starboard side. And so it's kept clear of anything. It's just about a water bottle sized piston looking arrangement. Fastcat Seabird 49 is what's fixed on the side there.
So yeah, it's right where the oil compensator is, but on the other side of the vehicle. So it's between the top vertical horizontals and the bottom horizontals. And we really haven't had any issues with fouling or any. The data's looked pretty good since we've been using it, to be truthful. So, but it's a small, like Sam said, it's a small one. The diameter is only 2 inches, and it's like 20 inches long or something like that. So it's not a 19 plus or anything.
Thank you. And her next question is: does the robotic arm weigh enough to require active ballasting while in use?
Yeah. So the robotic arm is actually it's aluminum housing and it's oil filled. And it's fairly heavy, but it's not underwater. It's not in the water. It's not that heavy. So everything we have, that if you look at this picture, the synthetic foam on the front of the vehicle used to actually stop like 8 inches further back than it does now. We can go back to the original first shot here. So in this yellow, the top one up here, you can see that it used to not come all the way out to this silver bar. Now it extends way further out. So right now, what we basically do, Sam and I do, we did last week before we're going to St. Thomas in 2 weeks, is we put dive weights on the ROV in the water, and we keep it about 4 pounds positively buoyant in case the umbilical were to get cut or something like that. So we always have it perfect. So when we're using the manipulator underwater, it doesn't really matter if we're using it. It's always about plus 4 or 5 pounds positively buoyant.
Oh, I like your last question. This is something I'm really interested in adding to the vehicle. Do you have any autonomous control? And I mentioned before that we don't have any, cruise control. Other vehicle systems are able to have, heading mode, gyro hold, things like that. We have these features that we could potentially be able to hook them together, but it's not something that we've figured out yet. But currently there are none, but it would be nice to figure out actually making them work.
Yeah, I think in order to do that, what we would need to do is purchase two things: a DVL, Doppler velocity log, and then INS, inertial navigation system. So, for us, we just can't buy those two things and throw them on the ROV. Then we have to get the folks who built the ROV to rewrite the software, so the software of the ROV ingests all that data, and then the auto functions would work properly. But as y'all can see, we've added a lot of stuff to the ROV, and we're kind of maxed out on space right now. So we don't have a ton of area on the ROV to add more stuff without losing either the collection capabilities or something like that. So it's pretty full currently.
Did you have another question? Got it. I have a couple more questions, maybe just one. I was wondering about the depth capability. Is it governed by, what is it governed by? The cable length? So right now you have, I think, a 300 meter max depth, and then you're hoping to go up to 1,000 at some point next year, maybe? So is it just cable length that is the issue?
Yeah, there's a few things that go into the 1,000 meter, but currently what we have that we'll be taking out this summer on the Pisces is a winch with a longer cable. So for that system, just being able to go to about 520 meters is our next goal, and we purely just have a longer umbilical cable. For the 1,000 meter system, it's a little bit different because of the line loss over the cable. So we can't just get a longer cable and be able to dive to 1,000 meters. We're going to have to make a smart downweight, something that will actually have a transformer at the downweight's location, which will be just about 100 feet back from the ROV. We have an armored cable, have a winch. There's a whole budget that we're putting together to be able to make it to a 1,000 meter system, which I'll let you elaborate on some more. Yeah, so
the electrical. So basically, the ROV manufacturer said we can go to 600 meters with our current electrical system, which is 440 three-phase AC voltage for the thrusters. That's what uses that. Everything else on the ROV uses single-phase 230. So with the thrusters, though, we lose too much power. They said if we go to 1,000 meters, we only get like 40% max power out of the thrusters, which Sam and I basically agreed that we don't want to be able to limit ourselves to that. So we got to increase it to 3,000 volt, three-phase AC power in order to do the 1,000 meters. So we'll get a different system control unit on the top side. We'll get the same voltage from the ship that will transform her to 3,000, go down to the smart downweight that she was talking about, and then get transformed back to 440 and go down to the ROV. So the ROV won't change at all. It's just the electrical between the ROV and the upside. So, but, yep.
Thank you. Ooh, okay,
Nice.
go for it.
If you want to go for it.
There's one more in the chat, I think.
Yeah, great talk. That's really interesting. Can you hear me?
Yes.
Yes, so thanks for that great talk. So I'm just kind of curious because I noticed that you are not using TMS. It's more of manual cabling, and so like what are some of the challenges you face with that, compared to you using TMS?
Yeah, we do. Yeah, this live boating method and not use a TMS or a garage. And it gives us a lot of capability for the unique things that we do. The transect lines we run 100 meters long, will run 300 meters long, even transects. And if we were to carry the TMS with us in the water column, it would provide a complication, to have so much movement. So I think a lot of operations that do have the TMS aren't moving as much as we are on the seafloor, doing as much exploration as we are. So that's one thing why we do the live boating instead of the TMS. But from the topside perspective, it means more work. It means more heavy lifting. It's not that heavy of lifting, but you're getting a better workout. Not that you're actually hauling the cable back as it comes aboard, But instead of, the reeling and winching capabilities of the TMS and just everything being bundled and foiled nicely, we're actually physically, manually, you saw, the videos of us cooling the umbilical into the box is more of the topside perspective differences.
And another point too is we can bring the ROV up and put it down really fast with our current system. So if you imagine if we want to go down to 100 meters and fill the box, everything up with samples, so we can get, if we get one species of sample and we got to separate them for DNA purposes, we can get like 10 samples at a time. So if we're going down and getting snips of Swifty or some other coral, go down, we can usually do that in 45 minutes, hour and a half, get 10 samples, and we can be back on the deck of the boat in like 10 minutes. And it's a lot less complex of the slip rings and all the complex parts of the TMS systems. We can bring it up, throw our spare things, bio boxes in the ROV, and 10 minutes later be back on the seafloor again, getting more samples. So we try to be really efficient for the scientists to get up and down quickly and unload the samples and get more samples and things like that. So.
Oh, that's interesting. Thank you.
And we got another question on the chat. It says, how do you usually interact with recorded data after acquisition? Especially, what is your way to visualize multi-beam and video footage? So that's a good question. So for multi-beam, what we do is we put that in HiPAC and we overlay the ship and the ROV on it, and we basically use it to drop the ROV. So we'll move the ship over a certain thing, and then we'll go over a certain feature with the ROV, and that's kind of how we move. Back before there was multi-beam, we would just use a chart. We would go over with the ship to a certain area. We'd figure out what depth it was, and we put the down weight 10 meters above that depth, and we would send the ROV down, and that's kind of what you figure. That's what you get. But nowadays with multi-beam, it makes our life a lot easier. Back in 2017, we did circumnavigation of Cuba. We had no multi-beam in the entire island. It took like 35 days, and we would just basically do a transect with the ship, figure out the depths, and then throw the ROV in and go up the wall. With the video data, so we don't really look at the video data, to be honest with you. So Sam and I's main job here is to allow science to take place, or you're better at this explanation than me.
Yes, it's hands off for us after we collect the data, which is our scientists, we try to make everything as streamlined as possible for them. But I know that they'll run their computers with the timestamps on them. They'll run, if they're doing a fish habitat survey, they'll take the timestamp off. Have you ever had the needs to synchronize the visualization and interaction of those two data sets? Unfortunately, we can't exactly answer that because we don't do any analyzation of the data after we collect it. So sorry that I can't answer that fully.
Yeah, we don't even keep a copy of the video, actually, because if you think about, this 2-week cruise we're going to go on, we're going to have 15 terabytes of data, and then we have another 70 days of cruises this year. So we get, if we were to keep everything, we're talking 50, 100 terabytes of data per year. And this program's been around a long time, so we just don't have anywhere to keep all that. So we honestly don't keep a copy of everything or much of anything.
What's your max endurance? I think your maximum dive time was 10.9 hours. Is that the max that you would want to push the ROV? Or, essentially there's no max because it's cabled. But.
Well, so another thing about our team, UVP, we're kind of unusual where it's just the two of us. So we're a 2-person team, and the way we do things is one person's inside and one person's driving, piloting the RV, doing the tracking, doing all that stuff. And then the other person is on the deck, and we switch every other day. So if I'm inside today, Sam's outside, and then the next day she's inside and I'm outside. So the biggest thing for us is we try to do that to make us as affordable as possible for scientists that can't, afford really large ROVs. So really the part for us for running really long is we just get worn out after a time. So especially since one person's driving it all day long. So typically we do 4 or 5 hours at the most, come up and take a little break, and then go down for another 4 or 5 hours. There has been several situations where we'll have to go in and we stay in the water all day long. And then the person on the deck will come and leave the other person for lunch and bathroom breaks and stuff like that. So, but technically, if we were hired 2 more people, we could run it 24/7 until something breaks, which wouldn't be too long because things break all the time. But, yeah.
Thank you. Is there one more question or that's any more? Okay. Thank you so much, guys. We appreciate it. Have a lovely weekend. It's good to see you again, Jason.
Yep. Thanks for having us, guys. Y'all have a great weekend too.
Thanks, bud.
Bye.